Hi friends, today we are going to discuss the topic electrolytic conductance for FIBSc chemistry student. Myself Ramdas Suralkar, Assistant Professor, Department of Chemistry, Pratap College, Amarner, Autonomous. The content of this topic are introduction, what is meant by electrolytic conductance, what are the factors affecting electrolytic conductance, what is meant by specific resistance, what is the working of conductivity cell, variation of conductance with concentration of solution, Kohlrausch law, application of Kohlrausch law, conductometric titration, and lastly the application of conductance measurement. Introduction. So metal conduct electricity due to the movement of electrons. Such conductivity is called as electronic conduction. The solution containing ions also conduct electricity. Such solution is called as electrolyte solution, and the conductivity in electrolyte solution is called as ionic conductivity. When electric current is passed through both these conductors, they obey the Ohm's law. That is I is equals to E upon R. So Ohm's law is stated as the current I in ampere flows through a conductor is directly proportional to the strength of the applied electromotive force E in volts and inversely proportional to the resistance R in ohm of the conductor. So the mathematically the Ohm's law can be stated as I is equals to E upon R. Then we will see electrolytic conductance. The conductance due to the ions produced by the electrolyte in the solution is known as electrolytic conductance. When current is allowed to pass through the electrolytic conductor, then it experiences the resistance. This resistance can be determined by applying Ohm's law. However, it is customary to measure the conductance instead of resistance. So conductance is reciprocal of resistance. So we measure the conductance of the solution. What are the factors affecting conductance? So there are three factors which affect the conductance of the solution. That is the concentration of the solution, temperature of the solution, and the nature of electrolyte. So concentration, as the concentration increases, the conductance also increases. Then temperature, higher the temperature increases conductance by enhancing ion mobility. So at higher temperature, the conductance also will be higher. So it is directly proportional to temperature. Conductance depends on the temperature. So as the temperature increases, conductance also increases. And also depends on nature of electrolyte. That is, there are two types of electrolyte, strong electrolyte and weak electrolyte. So strong electrolyte dissociate completely, and therefore conductance will be higher. And the weak electrolyte, they are partially dissociated, therefore their conductance will be lower. So conductance also depends on the type of electrolyte, that is the nature of electrolyte. Then what is meant by specific resistance? That is symbol is rho. The resistance of any conductor is directly proportional to its length and inversely proportional to its cross-sectional area A. Therefore, resistance R is given as. So R is directly proportional to length of a conductor and inversely proportional to area of the conductor. Therefore, R is equals to rho into L by A, where this rho is called constant of proportionality, and it is known as specific resistance of the conductor. The specific resistance is the resistance in ohm offered by the conductor having 1 centimeter length and 1 centimeter square area of cross section. So it is the specific resistance rho of the conductor. Then specific conductance K. So relation between specific conductance and specific resistance, they are reciprocal of one another. Therefore K is equals to 1 upon rho. K is called specific conductance of the solution. Instead of rho, we may write here L upon Ra. So specific conductance is the conductance of the conductor having 1 centimeter length and 1 centimeter square area of cross section. So K is the property of the conducting media. Then another term we will see, that is the equivalent conductance, that is known as lambda. Its symbol is lambda. So in case of electrolyte solution, generally equivalence conductance is measured. The equivalence conductance of an electrolyte is defined as the conductance of a volume of solution containing 1 gram equivalent of an electrolyte when placed between two large parallel electrodes which are exactly 1 centimeter apart. So equivalent conductance symbol is lambda is equals to specific conductance into V is the volume of solution containing 1 gram equivalent of an electrolyte. So instead of this V, we can put here V is the volume of solution containing 1 gram equivalent. Therefore, lambda is equals to 1000 into K by C. That is means equivalent conductivity is equals to 1000 into specific conductance divided by concentration. So what are the units of this equivalent conductance? Equivalent conductance is measured as in the units of moles centimeter square per gram equivalent or ohm inverse centimeter square per gram equivalent. Then we will see the conductivity cell. So the conductivity cell consists of two identical platinum electrodes. These are shown in this figure here. These wires are platinum wires and these are the platinum coated with platinum black. This platinum wire is coated with platinum black and they are at a specific distance from one another and its length is also specific. So for most of the cases cell constant is 1 for this conductivity cell. So there are different conductivity cell are there depends on the type of solution which is measured for conductance measurement. The conductivity cell are differently these two electrodes are separated differently depends on the requirement of the measurement of the conductance of the particular solution. Then what is meant by cell constant? That is called K. So cell constant is nothing but the length per unit area. So L is the length of the electrode platinum wire and A is the area of the platinum wire or electrode. So specific conductance equals to cell constant into observed conductance. L is called observed conductance. So specific conductance is equals to K into L, that is uh, observed conductance into cell constant. So cell constant can be determined by using standard KCl solution, that is for example 0.01 molar KCl solution at 25 degrees centigrade has a specific conductance of 0.001408 per ohm per centimeter. So we have to determine the cell constant of the solution and for that we need the value of specific conductance of KCl. So specific conductance of KCl has different values at different temperatures that are fixed values. So from this literature view we get this KCl values ranges from 25 degree to 38 degree centigrade. So as per the temperature we can use that particular value of specific conductance of KCl to determine the cell constant. So for this cell constant determination we need the to know the specific conductance of KCl and again by observing the conductance of the KCl solution in our lab we can determine the cell constant, that is the reciprocal of specific conductance of KCl at room temperature upon observed conductance of KCl at room temperature. In this way, from this ratio we can determine the cell constant of any particular cell. Then how this electrolytic conductance may be equivalent or specific conductance, how it can affected by means of concentration of solution. So this is the graph of concentration versus equivalent conductivity. So we get two different curves for strong electrolyte. The curve is smoothly decreasing and for weak electrolyte it is decreasing at sharply and by as the concentration become increase more and more the conductance decreases slowly. So from this curve from this strong electrolyte curve if we extrapolate this strong electrolyte curve on y-axis we get equivalent conductivity at zero concentration or infinite dilution, means this is the origin and at origin the concentration is zero, means the solution is very dilute and at zero concentration of solution, or at infinite dilution of a solution for strong electrolyte, we can obtain this uh, limiting value of equivalent conductivity at zero concentration or at infinite dilution. But in case of weak electrolyte, we cannot extrapolate the graph to obtain this lambda 0 value or lambda infinity value. So for the conductance at infinite dilution or zero concentration for weak electrolyte cannot be extrapolated from this graph, and this can be solved. So to determine the equivalent conductivity at zero concentration or infinite dilution, we need some another law that is called Kohlrausch law of independent migration of ion. So Kohlrausch law of independent migration of ion state that at infinite dilution, where dissociation is complete, each ion, it may be cation or anion, makes a definite contribution to an electrolyte's total molar conductivity, independent of the presence of other ions. The limiting molar conductivity of an electrolyte is the sum of these individual ionic contribution. So, according to this law, at zero concentration or at infinite dilution, the each ion has their own contribution towards the conductance, and it does not depends on the concentration of the partner ion. That is, for cation, it has its own contribution toward the equivalent conductivity at infinite dilution or at zero concentration, because its partner ion, that is negative ion, is far apart from one another at dilute solution, and therefore each ion has its own contribution toward the equivalent conductivity at infinite dilution or at zero concentration. So mathematical, this equation can be written as at infinite dilution, lambda 0 is equals to lambda 0 cation plus lambda 0 anion. So the equivalent conductivity at zero concentration is equals to the sum of ionic conductivities of both the ionic partners, cation and anion. So it is the sum of two conductivity of two ions that gives the equivalent conductivity at zero concentration. Independence. At infinite dilution, ions are so far apart that they do not influence each other's movement toward the electrodes, allowing for the independent contribution. In this way, they are not they have their own contribution toward the conductance of the solution. What are the application of this Kohlrausch law? We can calculate the limiting molar conductivity, that is lambda 0, used to determine the lambda 0 for weak electrolyte, that is for acetic acid, that cannot be found by direct extrapolation. So we have seen in the previous slide that for strong electrolyte we can extrapolate the graph and obtain this lambda 0 value uh, for at zero concentration, but for weak electrolyte like acetic acid we cannot extrapolate that graph. But by using this Kohlrausch law of independent migration of ion, we can calculate the equivalent conductivity at zero concentration for weak electrolyte also, like acetic acid. Means acetic acid can be ionized to form acetate anion and H plus ion. So acetate anion has their individual contribution, as well as H plus ion also has their individual contribution. So sum of these two ions gives the total ionic conductivity at zero concentration of this weak electrolyte. So in this way we can calculate the limiting value of equivalent conductivity at zero concentration. Another application of Kohlrausch law is conductometric titration. So we can do the conductometric titration for weak acid strong base reactions. So because weak acid, they are easily get in normal acid base titration, they get neutralized in 1 to 2 drops of base. That's why the exact equivalence point cannot be measured by our regular uh, titrations. So these conductometric titrations are very useful to determine the exact equivalence point of the titration. It can be also used to determine the degree of dissociation, that is alpha. So alpha can be calculated, that is equivalent conductivity of at any concentration upon equivalent conductivity at zero concentration. From this equation we can determine the degree of dissociation. Another application is calculating the solubility. So it helps in calculating the solubility of sparingly soluble salts. The salt which are not easily soluble in water, that salts are called as sparingly soluble salt. So they are not easily soluble in the water, and therefore their solubility can be measured by using this Kohlrausch law, by measuring the conductance of that solution. From this conductance we can determine the solubility of this sparingly soluble salt. Then we will see the conductometric titration. So in that we will see first the titration of strong acid with strong base. So this is the practical for FIBSc chemistry student. In the physical chemistry practical, they have this titration on conductivity meter. So conductometric titration of strong acid versus uh, weak acid, sorry, strong acid versus strong base. So for conductometric titration of strong acid with strong base, determine the equivalence point by measuring the changes in the electrical conductivity as ions high mobility are replaced by ions with lower mobility. So in case of this strong acid versus strong base titration, the highly mobile H plus ion are replaced by low mobility OH minus ion. Therefore, this equivalence point can be measured. So which decreases the conductance. A V-shaped curve is produced with the minimum conductance marking the equivalence point, after which ions causes the conductivity to increase. So after this this is a V-shaped graph. From this graph we can draw perpendicular on x-axis, and from that volume of NaOH we can determine the equivalence point of the titration. So principle of behind this titration is what is the reaction? HCl plus NaOH gives NaCl plus H2O. So neutralization reaction takes place and salt and water are produced. Initial state: high conductivity due to the presence of highly mobile H plus ions. During titration, as NaOH is added, H plus ions are replaced by Na plus ion. Because sodium ions have lower ionic mobility than the H plus ions, the overall conductivity of the solution decreases. So initially, during titration, the conductance of the solution decreases as we add the NaOH ion, and so H plus ion, they are highly mobile ions, are replaced by slower mobility ions Na plus ion. Therefore, conductance get decreased. Equivalence point: the minimum conductivity is reached when all the H plus ion have been neutralized. When all the H plus ion are neutralized by NaOH, then at that time conductivity, minimum conductivity is observed. Post equivalence point: addition of excess NaOH adds Na plus and OH minus ions, causing the sharp increase in conductivity. So after neutralization of H plus ion by NaOH, OH minus ion, we add excess NaOH, and because of addition of excess NaOH, Na plus and OH minus ions are produced. These OH minus ions are highly mobile ions, and because of that the conductivity again going to increase. So in this way we can determine the conductivity of equivalence point of this type of titration which is accurately determined. Another titration is conductometric titration of weak acid with strong base. So we can do the titration of weak acid also. So the conductometric titration of acetic acid with sodium hydroxide result in a graph where the conductance initially increases slowly due to the formation of salt sodium acetate, followed by a sharp increase after the equivalence point due to the presence of excess highly mobile OH minus ions. The equivalence point is the point of intersection of these two linear segments. So initial conductance: pure acetic acid shows low conductance from partial dissociation into few H plus and CH3CO minus ions. H plus ions contribute most despite low numbers. During neutralization, NaOH addition neutralizes the acetic acid. So reaction is acetic acid plus NaOH gives sodium acetate plus water. So weak acid converts to strong electrolyte sodium acetate, raising the conductance moderately via more acetate and Na plus ions. After equivalence point, excess NaOH adds highly mobile OH minus ions, causing sharp conductance increase. The curve shows a moderate slope line meeting a steep ones. Equivalence point detection. So plot the conductance versus NaOH volume V. Intersection of the lines mark the point This V reveals the acid concentration. So in this graph, if we observe this graph of conductance versus volume of NaOH, initially the conductance, when we add the NaOH solution to the acetic acid solution, the conductance increases slowly due to the formation of highly mobile sodium acetate salt. They have high conductance value and therefore conductance increases slowly. But at neutralization, during neutralization of this acetic acid by NaOH, the rise in conductance is observed is very high. The value rises because of the addition of OH minus ions from the burette. So these OH minus ions are highly mobile ions, and because of that, this in this way we get two different lines, and the intersection of these two lines gives the equivalence point of the titration. What are the application of conductance measurement? So conductometric titration, by doing conductometric titration, monitoring the conductivity changes to find the endpoint for titrations, especially used for colored solution or weak acid or bases where visual indicators fail. So in this way, for colored solution, we cannot do the titration by adding the indicator. So in that case, we cannot observe exact color change of the indicator. Therefore, for colored solution as well as some weak acid or weak base titrations, they are very weak acid or base, so endpoint comes in 2 to 3 drops. That therefore we cannot determine exact equivalence point of that titration. In that case, conductometric titration is useful. Then we can determine the ionization or dissociation constant of acid or base or water. So determining the dissociation constant Ka, Kb for weak electrolyte and the ionic product of water by doing this titration. Solubility, we can calculate the solubility and solubility product of the sparingly soluble salt. Hydrolysis, we can determine degree of hydrolysis and hydrolysis constant for particular salt by measuring the conductance. In this way, we have finished this electrolytic conductance chapter. Thank you. Thank you, friends.